Hey everyone, welcome back to Math 7195, Unit 5 Reliability video. Today we're going to discuss series versus parallel. We'll talk about reliability where there's a time dependence, and we'll use various probability models to represent our reliability over time. Basically, this unit is an application of things that we've done before. So there's nothing technically new in this entire unit. It's just a nice uh, showcase of things that we've already done. We'll get to see uh, our distributions sort of in action with nice practical applications. So let's dive right in. Unit 5 on reliability. We start out with the basics of reliability by discussing uh, the topics of series and parallel. When you have a bunch of components that are basically in line, we'll describe this system as being in series. And one of the properties of this system is that if any part of it breaks, the whole thing breaks. So if you break the line at any point, uh, you have failed. So when we're talking about this sort of thing, uh, we'll look at it from a positive point of view rather than how to break it. We'll talk about its reliability or its probability of being successful. I'll just give you some notation here. I have some components A1, A2 up to AN, and I need all N components to be reliable in order for this system to be good. Notation for that, I'll use R for reliability and a subscript S to indicate that it's a system that's in series. It's only reliable overall if all the pieces are good themselves. So if we define each piece has its own reliability, in order for the whole thing to be reliable, we just need the product of those reliabilities. We need a good one, and a good one, and a good one, and we're just multiplying all those together. Some notation here. You've seen summation notation. Maybe you're not as familiar with this product notation, but it just means to take the product of these individual reliabilities. If we're interested in the unreliability, what's the probability of such a system failing? Then we just can simply do 1 minus the reliability. Because to try to calculate the unreliability directly would be difficult because there's many ways it can fail. If the first piece fails, it fails. If the third piece fails, it fails. If the first and seventh piece fails, it fails. So determining the unreliability directly is difficult, but determining the reliability is easy. My grandma's Christmas lights were in series like this, where if one of the light bulbs went out on her tree, the entire string went out. And it was a nightmare to try to figure out then, which one was out, because now they're all out. So, you had to do some systematic testing with a known good bulb in order to figure out, what was wrong with the whole string. That seems kind of silly now. Uh, you know, Christmas lights are designed much better than that. But many things still are in series in some way or another. Like the lecture that I'm giving to you right now, I could think of it as a series of components that I need to make this work. I need the recording program to be working. I need my microphone to be working. I need the video to work. I need my tablet stylus to work. I need OneNote to work. If any one of those things goes down, well, then this lecture is, in the garbage. So it's not, that it's easy to come up with examples of things that are in series and then try to measure their reliability. In this example, I haven't factored in time at all. I'm just talking about an instantaneous, like what is the probability that my lecture will fail right now? You're probably hoping high. And there are a lot of moving parts, so it's possible. Here's a little example. I have a wall. It's being held up by 4 pillars, and they aren't very good on their own. If any one of the pillars fails, the whole thing collapses. And we know that the reliabilities, actually, we're given the probability of them failing. If I number these 1, 2, 3, and 4, I know the failure probability of column 1 is given there at 1%. And the failure probability of column 2 is 5%. And they told us the probability of column 3 failing is 1%, and the failure probability of column 4 is given at 10%. Somehow they, examined these columns and were able to determine these probabilities under some certain conditions, like there's going to be an earthquake. Now, if we want to know the reliabilities of each one of these, I guess we just do 1 minus. So the reliability of the first column is, 99%. And we can do that for all of these. 95% reliable for column 2. Column 3 is also 99%. And column 4 is the rotten one. It's only 90% reliable. You can even see it has this big chip in it. Let's determine the overall reliability of this wall. Now, it was told to us that it will collapse if any of them fail. So if 1 fails, it fails. If 1 and 2 fail, it fails. If all 4 fail, obviously it fails. So this is in series. The reliability in series is just the product of the individual reliabilities. In this case, we have 4 columns, and we're just going to multiply those individual reliabilities together. I know my answer is going to be less than 90%. I mean, it can't be more reliable than its weakest part. So when we calculate this thing, I'm expecting something under 90. Taking out my trusty calculator, I get 0.8379855. So roughly 84% reliable, if you trust the initial, assessments of the individual components. So that's a system in series. Kind of a crude example, but gets the job done. Sometimes we have components that are in parallel. Now, when we have a parallel system, we have alternatives. So if part of it fails, the rest of it takes over. And we have to make some assumptions that if part of it fails, it doesn't change the reliability of any of the other parts. There would maybe be more strain on the other parts, and therefore they might be slightly more unreliable. But let's make the assumption that each component is independent, just because it would be, in most situations, we couldn't measure the interdependency anyway. So at least we'll get a lower limit here. So when you're talking about parallel, it's easy for it to be reliable because you just need, one path to be successful. You could have a whole bunch of failures, but as long as one piece of it is still up and running, the thing is still reliable. So it's actually harder to view it from its reliability standpoint. It's easier to think about these things when they're unreliable, because there's only one way it fails. That's every single piece breaks. If all the components break, well, then you can't get from here to here. So we'll examine these parallel systems sort of negatively. We'll study them, unreliable, their unreliability. I'll denote it as F sub P, the failure of a parallel system. It's just the product of them all failing. So to fail in parallel, I need every single piece to fail. Fail and fail and fail and fail, which just means multiply all the failure probabilities together. If you then want the reliability of a parallel system, we'll just do 1 minus the failure. So reliability is 1 minus failure. So it's actually easy to do. It's just as long as you think of the right approach when you're attacking the problem. An example, we're back to our ancient wall. It still has the 4 columns. But now each pillar is going to be capable of supporting the entire wall. So if three pillars collapse, the remaining one will still hold up the wall. So now we want to know the reliability of this sort of system. This is vastly superior to the previous wall. We left the probabilities all the same so that we can compare the two. Column 1 had a failure rate of 1%. Column 2 had a failure rate of 5%. Column 3 failed 1%, and column 4 failed 10%. So to figure out the probability that the whole thing fails, the failure of the system in parallel is just going to be the product of the individual failures. And we have 4 pieces. So we'll have 0.01, 0.05, 0.01, and 0.10. That's the probability of it failing. And then to get our reliability in parallel, we'll just do 1 minus the failure. So 1 minus that product, and we get 0.999995. Very, very reliable. Even though the individual pieces aren't that great. 1% failure rate, 5% failure rate, 1%, 10%. But if you put 4 of them together, you get something that is very reliable. The math department at BCIT, we have 4 printers. They're always breaking down in one way or another. So they have a relatively high failure rate individually. But the chances of me being able to print out your midterm are pretty high because at least one of them should work. And you can see the power of this. I mean, it's almost certain that this wall will survive even though the 4 individuals aren't that great. So it's a situation, or it's a reminder that sometimes you can buy, 4 cheap items rather than one really expensive item. And overall, you'll do much better with the 4 cheap ones than the 1 expensive one. I was watching a documentary about landing on the moon in 1969, and they said that the Saturn V rocket that took man to the moon, had over 3 million parts. So imagine each part is 99.9% reliable, which that probably is a very high estimate, actually. 99.9% are reliable, so 0.1% are unreliable. So 0.1% of 3 million parts is 3,000 pieces are expected to fail. It's crazy. Uh, I Googled how many parts there are in a standard, you know, airplane, and it's like a million. And you know that they aren't 99.9% reliable. However, I mean, most of those parts aren't essential, for the thing to stay in flight, which is, you know, somewhat reassuring. But it's still kind of scary that, we send things to the lowest bidder, and we probably don't necessarily have these sorts of reliabilities. Uh, that's why you build redundancies into systems, right? You know, on your airplane, there are probably 4 or 5 ways of getting the landing gear to go down. There's the standard press a button, then there's the backup button, then there's a lever, and then there's some manual crank. And so you can feel pretty good that at least one of those things is going to work, and therefore you can get the landing gear down and be able to land. So yeah, parallel is really powerful. Be careful, I can mix these two topics together. I could draw you a picture like this, say, where you have to get through this path, and then we could find the reliability of this sort of system by analyzing it sort of piece by piece. Find the reliability of this parallel section. And then once you know the reliability of the parallel system or section, then you can view the thing in series and consider it, piece one, piece two, piece three, and this whole piece is now just one reliability. So rather than trying to trace all the different ways that you can get through this, you can essentially just kind of attack it bit by bit. Oftentimes I put one of those on a test, so keep your eye out for such a thing. You're basically just combining the two examples that we just did. We can factor time into this now. Um, let's define t as a random variable as the time to failure. And then we can start defining the probability of lasting a certain length of time. What's the probability that my new smartwatch will last more than 2 years? What's the probability that my smartwatch will die in the first 6 months? Uh, if we can model the distribution of those failures, then we can start to estimate these probabilities. And we can come up with different probability distribution models to, to show these things. We discussed, the normal distribution, the exponential distribution, the Weibull distribution, the log normal distribution. We can use those various models to, well, basically model any, sort of, gadget we're interested in. So we'll define R of t as the reliability of lasting at least t hours, days, months, whatever the units are. So we can define R of t as the probability of some random variable big T being greater than some amount of time. And we can define unreliability as then the complement of that. So we just need to know the function for a certain situation, and we'll basically be finding the area beneath the curve to get these probabilities. We can talk about the average length of time that something will last, the mean time between failures or the mean time to failure. These two terms are used sort of synonymously. The mean time to failure is when something fails and it's just disposed of. The mean time between failures is used when we're talking about something that fails but gets fixed. The average time between my car failing, for example. It follows its expected value. It's the expected amount of time that the thing survives. And we use the same formula that we used for expected value when we were discussing any continuous distribution, except I made the lower limit time starts at 0. Like typically we were writing this as minus infinity to plus infinity, but it's the same. We'll just have to do some integration to find the average length of time. On average, how long does a smartwatch last? For example, this is important if you're, the person who's setting up warranties, for example, or if you're somebody who's analyzing different smartwatches and trying to decide, which one is, say, better. There's this integral is often hard. This integrating t times f of t. Oftentimes we have to do it numerically, just because the functions tend to be difficult. There's kind of a neat identity that if you already know the reliability function, like if you can model the reliabilities, then this integral is easier to handle. And to show that this is true, you just do a little substitution. You let u equal r of t, and we're going to take the right side of this equation and show that it equals the left, because it's not intuitive. If I just look at that, that doesn't really make sense to me, but it's curious that it works. And you can show it by taking, in this case, you actually start with the easier side and you make it look like the more difficult side. It takes a little bit of calculus, but it's not too bad. If you let u equal r of t, then du is r prime t dt. And let dv equal the other piece, the dt. Then if you integrate that, v will equal t. And remember, integration by parts, you get uv minus the integral of v du. So if we start with our r of t dt here, we can replace it with uv minus the integral of v du. So in this case, our u is r of t, and then our v is t. And we're evaluating that from t equals 0 to infinity. And then we're subtracting the integral of v du. And du is this r prime t dt. And we're doing that from 0 to infinity. So we've really made a mess out of this thing, but it's actually not too bad. Believe it or not, we're almost home. We'll have to do a little trick here. Remember, there's a relationship here. F of t is 1 minus r of t. The failure probability is 1 minus the reliability. If we take the derivative of both sides of this thing, you get negative r prime t. Well, something interesting about that, capital F is the integral of little f. That's the fundamental theorem of calculus. So we can replace this f prime of t with little f of t. Whatever that function is. So we know now that little f of t equals r prime, actually negative r prime of t. And now check this out. We can substitute this thing back in there. I'm just going to rewrite this, and I'm going to switch this around. I don't like the order of that thing. T times r of t from 0 to infinity minus, I have negative r prime of t equals little f of t, so I can just substitute that in there. I have a minus sign out in the front, so I can change that to plus. And now I have little f of t. If you look up above, that's what we're trying to show. We're trying to do, t times little f of t. So we're actually pretty much done with this as long as we can convince ourselves that this piece here ends up being 0. Now, if you evaluate this thing at infinity, you get infinity times the reliability of infinity. Basically, think of this as what's the probability that something lasts infinitely long, which would be 0. So we'd essentially have infinity times 0, but the reliability would be the probability of lasting an infinite amount of time would approach 0 faster than t would approach infinity. So that means that this piece would essentially go to 0. And if we plug in 0 for this thing, obviously 0 times what's the reliability at time 0? The thing either it's perfect, so it's 100%, or maybe it isn't, which means it's also 0. So this is 0 in that case as well. So t times r of t as t goes, maybe I should write, maybe I could write that. The limit as t goes to infinity of t r of t minus plug in the 0, and then we have the other piece. And I think we argued that this piece has to go to 0 because the r of t will go to 0 faster than t goes to infinity. And this is either 0 or it's 1, but either way, it's going to be 0 times it. So we get 0 minus 0 plus this, which is what we were trying to prove. So we can use this identity now. There's certain times where if we want to calculate the average time to failure, we can just integrate the reliability function. And maybe we'll see an example. Another feature of these things is the failure rate. This is a ratio. It's the proportion of devices failing right now divided by the proportion that are remaining. How many devices are failing right now out of all the possible that are still alive? So we could basically think of this as an integral over a short range. Right now is like, a millionth of a second, for example. So a short interval, which is just a skinny rectangle. So it's the height of the function times that short interval. And then we want to divide that by the number that are still remaining, which is the ones that haven't failed, or the reliability. So we'll define this as the hazard function. It's that proportion of those that are failing now to the ones that are still remaining. And the formula for this will change depending on what model we're using, but the shape of the thing will typically look something like this, where here is the failure rate function. At the beginning, you have a high failure rate. When you first come off the assembly line, there are defects and such that haven't been caught yet, so a bunch of them fail initially. But then after you have them fail, well, now you have a nice stable supply of your widgets, and they will sort of fail at a constant rate due to outside traumas that are just randomly occurring. I have a brand new cell phone. New cell phones are coming off the assembly line, and a bunch of them have problems. They don't work right away, or they don't work they'll break in the first 10 minutes. But after they survive for a few minutes, there's a good chance that they'll last, quite a long time. And they'll just be breaking due to, random things happening to them. But then after they've been around for a long time, well, then the failure rate starts to increase. Once my cell phone is 3 years old, things start to wear out. The battery isn't as good anymore, and we have that failure rate starting to increase again. So we have a decreasing failure rate at the beginning, then kind of a constant failure rate through the middle of its life, and then an increasing failure rate at the end of its life. Sort of a burn-in uh, failure rate, then sort of a constant failure rate, and then an increasing failure rate. They call this the boat shape. Uh, I guess it sort of looks like a boat. So now let's start talking about the functions themselves. We're pretty familiar with the normal distribution. We could use that to model the reliability of a device. This is a case, where some object has a property of mostly failing around the average length of life. Not many fail at the beginning. There aren't many left at the end. So you get that bell curve shape. An exponential failure model, has that sort of a memoryless property where it has a constant failure rate. So we often use this for electronic devices. Electronic devices, they don't have a lot of moving parts, so they don't wear out in, the sense that, you know, the moving parts of my car might. So like a light bulb, for example, often has an exponential failure model because the thing could be burning. Could have a light bulb lit for 100 hours, and it's no more likely to die than one that had been burning 200 hours or at 300 hours. Uh, they tend to burn out due to outside factors until they get to a certain age, and then of course they become more susceptible to burnout. But at least during that middle portion of their life, the exponential function models, electronic devices quite well. Remember, we had the exponential distribution function. This is the PDF, probability density function, and we integrated that thing. If you integrate this thing, we could get the area beneath the curve. So the integral or antiderivative of little f is big F. And we did this in the previous lecture. And we can also do the reliability then, which is 1 minus failure. And it's even nicer in terms of, what's the probability that something lasts 10 hours or more? You just plug in 10 for t. And as long as you know what the rate is for beta, you can get the failure rate. And that's kind of what's interesting about the exponential function or exponential distribution. As I said, it does have this constant failure rate property where I put little f on the top and big R on the bottom, and you'll see that the exponential part cancels and you're just left with this constant rate. So those are two models. We could also use the Weibull function, which we didn't talk about that as much. The shape of the Weibull distribution depends on two parameters. And because of that, you can model many different things with the Weibull function. We did integrate it. The integral of that thing isn't too bad. So, and this is given to you. We'll have it on our formula sheet. There's also a Weibull function in Excel, just like there was an exponential function and a normal function, and you're welcome to use them. Just be careful about the Weibull function in Excel. Its parameters are slightly different than ours, and in the lab you'll learn what the difference is and how how to actually use the Excel Weibull function. But there's a template out there, so you'll be able to figure those out. The Weibull distribution, if you look at its hazard function, remember, Z of t is little f over big R. It's the proportion failing right now to the percentage that are still remaining. So I just substituted little f in and capital R in, and you'll see that you get some nice cancellation there again. So the failure rate can be expressed as the parameter alpha times beta times t raised to the beta minus 1. If we look at this thing a little bit, if t is if beta equals 1 in this equation, you just get alpha beta t to the 0, which is, and beta is also 1. I guess I could have replaced that too. That's, when, I guess it says it right here. When beta equals 1, we have alpha z at any time is alpha times 1 times t to the 0, which is just alpha. So a constant failure rate. And remember, we said that the Weibull distribution was a more general case of the exponential distribution. So technically, we don't even need the exponential distribution if we have the Weibull. It's just a Weibull distribution with beta equals 1. That's what an exponential distribution is. When beta is greater than 1, if you have this alpha beta t to the alpha minus 1, if you put in a value bigger than 1 here, well, then you have, say, you have t to a value bigger than 1. So it's like a polynomial, which is an increasing function. So your failure rate is increasing at that time. But if you put in a value smaller than 1, say between 0 and 1, then that's an x. Oh no, it's beta, isn't it? If you plug in a value between 0 and 1, you get t to a fraction. It'll be negative even. So it'll be like alpha beta over t to a power, which is something that's decreasing. So basically, we can model the whole life of a product using the Weibull distribution if we can figure out the function. In the middle of this thing is when we have constant failure rate. At the end of its life is when we have a failure rate that's increasing, so its beta parameter will be greater than 1. And then at the beginning of its life, the beta parameter will be some number between 0 and 1. So basically, we can use the same Weibull formula, but just keep changing beta depending on what portion of the life of the product we're in. Basically, define this thing piecewise using the Weibull distribution with different values of beta over different time periods. So we can basically model an entire product's life using the Weibull distribution in many, many instances. To come up with the parameters alpha and beta, now that's the hard part, the real life part. In a math course, we just say, oh, suppose a product has parameters alpha equals 6 and beta equals 1/2, and now we do all our calculations. But they never really go into how do they come up with those values. Well, to do that, you'd have to collect a bunch of data first. Keep track of when these things are failing. You do have a lab on this coming up. It's not this lab, but it's in a little while, where you get to actually do an example where you can come up with, what is the value for alpha and beta. For now, We'll just do it the old-fashioned way of somebody's going to tell you these parameters. In the exponential, what's beta? I don't know. And in the Weibull, what's alpha? What's beta? I don't know. But even for the normal distribution, it's the same thing. The parameters just don't seem as weird because we're talking about mu and sigma as our, the things that vary the normal distribution. We'll do a little example here. Suppose I have a device that on average lasts 500 hours. We'll do a bunch of examples now using the different models. Like, let's suppose our failure model is a normal distribution with a mean of 500. Then let's suppose it's an exponential distribution with a mean of 500 hours. And then let's suppose it's a Weibull distribution with a mean of 500 hours. And we'll just do the problem, a few examples. Let's just repeat these three questions. Let's find the reliability of 800 hours. That is, what's the probability that our device lasts more than 800 hours, given that on average they last 500 hours? Or let's determine the median life. What is the amount of time where 50% of them fail? If 50% lasts longer than that time, or 50% lasts less than that time. And let's also get a little bit of that hazard function mixed in there. Let's calculate the rate of failure when we're at that 800-hour point. So let's do did I do the exponential model first? Looks like. I guess it's the easiest one. So for the exponential function, the mean of an exponential is just that parameter beta. So whatever device we're studying on average lasts 500 hours. So our parameter beta is 500. The mean is the beta. And that's something that you could come up with experimentally, pretty easily. Keep track of your product for a while, see what the average life is, and say it turned out to be 500 hours. Now let's go with that. Let's call our parameter beta 500 hours. In that, we can find then the failure rate. There's one failure per 500 hours, or 0.002 failures per hour. I plotted the curve here just for your viewing pleasure, because we're trying to answer a few different questions here. We want the probability that the thing lasts longer than 800 hours. Remember, for the exponential, the reliability at any time t is e to the negative t over beta. You may remember that f of t was 1 over beta e to the negative t over beta. And that's what this curve is that I've drawn. That's the little f. Now r of t is the area beneath the curve. So we want to solve, I. It was the question, what are the chances that one of these things lasts longer than 800 hours? Which is r of 800. Which corresponds to, zoom in on that thing. Oh, there we go. We're looking at where t is 800, and we're finding the area underneath that curve above 800. So that's what this r of t is. It's the area. Maybe I should use a different color. Well, it's such an easy formula, which is why I guess I chose this one first. You just plug in 800 for t and substitute in your beta. So it's e to the negative 800 over 500, and your probability ends up being 0.2019. You gotta love the exponential problems. Let's try to figure out where the median of that thing is. At what point, let's call it M for median, huh? At some point here, there's a median where 50% are below and then 50% are above. We want to find that spot. We want to know the probability that T is, well, why don't we do greater than? Let's say the probability of lasting longer than the median is 50%. So R of M is 0.50, and we just need to figure out what M is. We have e to the negative m over beta, which in this case is 500. And now we just solve that equation, do a little natural log of both sides. Negative m over 500 equals the natural log of a half. So m is negative 500 times the natural log of a half. And I get 346.6 hours. Notice that the median is quite a bit smaller than the mean. And I didn't draw it very, I was just eyeballing that thing. I guess I should have drawn my arrow. The median's around there somewhere. Because I want 50% of the area going to the left and 50% of the area going to the right of it. And then the third question we were going to answer is, at what rate is this thing failing when T equals 800 hours? So at T equals 800, how fast are these things failing? So we want Z of 800. But for the exponential function, they have a constant failure rate. It ends up just being 1 over 500, or 0.002 failures per hour. At any time, these things are failing at that rate if we're using this model to represent our product that lasts on average 500 hours. Now this function here, if you're wondering where this came from, remember it is Z of T is little f of T over big R of T, which is given right up here, and that just turns out to be 1 over beta when we're talking about the exponential distribution. So there we go. We answered 3 questions if our product has an exponential model. What if we change it up a little bit and say, hey, we have a product that lasts 500 hours on average? But now it follows a normal distribution. So, there aren't many failing right at the beginning and there aren't many failing right at the end. Most fail in the middle of its life. In order to use a normal distribution model, we're also going to need a standard deviation. What bell curve should I draw here? So we could gather a bunch of data and calculate the standard deviation for our data and hope that that data is representative of the whole population. And in this case, I decided that our standard deviation for the product that we're making up is 150 hours. But again, it wouldn't be that hard to come up with this number, even in a real world situation. Just do a little pilot study, and you'll get at least in the ballpark for this. And then as you go along, you can revise the model. So back to our questions again. We wanted to know what's the probability of this thing lasting 800 hours. It's 800 or more hours, not exactly 800 hours, because the probability of something lasting exactly 800 hours is 0. We're looking for the area beneath the curve here, to the right of 800. That's the probability that t is greater than 800, which, if we're using Excel or a Z table, we would want to do the complement of this anyway. We'll do the unreliability. So 1 minus the probability that t is less than or equal to 800 hours. And then we have to calculate the z-score. Remember, z is x minus mu over sigma. So we'd have 1 minus the probability that t is less than or equal to 800 minus our mean of 500 hours. And we estimate that the standard deviation is 150 hours. That gives a nice z-score. It's 1 minus the probability that z is less than or equal to 2. And then we can just look up 2 in our z table. Zip over to my handy z table. We're doing 2.00, so we're in this first column here. So our probability is 99.72%. 1 minus that. So we get 0.0028. Actually, I feel like I got that number wrong. 9772. Yeah. Let me go back. Let me fix that. It wasn't 9972. It was 9772. I think I may have said it, but I review the tape. I remembered it as 9772. Anyway, so it's 0.0228. So the probability of lasting 800 hours or more is relatively low here, where in the exponential, it was a pretty high number with the same mean. Of course, if we messed with the standard deviation, we could, improve on this. If we made our standard deviation larger, then certainly this probability would increase. We're going to do the median. What's the probability of lasting? Probably easier to do it from a less than. Less than the median is 50%. Well, I don't even need to look this up in my Z table. Because the distribution is symmetric, the mean equals the median. So we're going to be 500 hours. So we don't have to really do any math for that one, as long as we understand that the mean and median are the same for the normal distribution. The failure rate function is a bit of a bear to deal with for the normal distribution because the function for the normal distribution was kind of ugly. You did graph this once, I think in your very first lab. It's little f of t over r of t, which little f was ugly. It's 1 over the square root of 2 pi times sigma times e to the minus 1/2 times the quantity x minus mu over sigma quantity squared. And then we have to divide that by r of t. So we're trying to solve this equation when t equals 800 hours. So we just basically substitute all our pieces in here. We know what sigma is. We know what mu is. Our x or t, I guess I should have maybe written a t there instead of x, since that's our variable. T. And then divide it by the reliability at 800 hours. So luckily we already know the reliability at 800 hours. We know R of 800 from up above. So that's that 0.0228. And then the numerator is just that ugly thing. 1 over the square root of 2 pi times 150 for the standard deviation, e to the minus 1/2, 800 minus mu, which was 500, over sigma, which is 150. I think that quantity is squared. And then divide all that by 0.0228, the R of t. Luckily, I already calculated that. It's 0.01579 failures per hour. At that instant, at time 800, they're failing at a rate of 0.015 units, 0.016 units per hour. So the failure rate here was, say, it was 0.02. They're much higher than they were for the exponential, which had a lower failure rate at that same time. We can use the Weibull distribution to model the same situation once again. This is the last example for this one. We're still going with, the mean life is 500 hours. We're sticking with that. Now, in order to use the Weibull distribution, we need to know alpha and beta. Now, in this situation, let's say, we're just going to make up a number here because we don't have the we don't have the data to try to come up with these values on our own. But to do an example, let's say, suppose we're interested in something that has an increasing failure rate. So in that case, the beta parameter for the Weibull distribution would be something bigger than 1. So let's just pick something bigger than 1, a nice number that we can deal with. Say beta is 2. Now we have 2 of the values. We know beta is 2, and we know the mean life is 500. So let's figure out what alpha would have to be if beta is 2 and the mean is 500 hours. So it's not going to be that easy. You probably don't recall from the previous lecture what the mean of a Weibull distribution is. I'll remind you, if I go back to our unit 4 notes, I'll make it dizzy sliding. We did Weibull right at the end. I did tons of normal distribution. We did log normal, we did exponential, and then we hit this Weibull distribution. And here's the function. And if you integrate that thing, you can determine the mean of a Weibull distribution. It's alpha to the minus 1 over beta times gamma of 1 plus 1 over beta, where gamma is defined as this ugly integral. So we have our work cut out for us here. Let's try this, see what happens. I just saw that the mean was alpha to the negative 1 over beta times gamma of 1 plus 1 over beta. and we know mu. So we know the 500 goes here. And we're trying to figure out alpha given, we just sort of pulled a number out of the air for beta. So this is kind of a made up example. But if we were able to estimate at least one of them and we knew the mean, then we can get the other. But we have to fight through this gamma stuff. Gamma of 1 plus 1 over 2. If that's the case, then we have, oh geez, gamma function. Too bad that's not an integer. Gamma of an integer is just the factorial of it. Gamma of psi was psi minus 1 factorial when psi was an integer. I guess a positive integer. Bigger than or equal to 1. But we don't have that. We have 1 plus a half. There is a neat property of the thing because of, this factorial nature. You can write it as psi minus 1 times gamma of psi minus 1. That might be helpful to us. But ultimately, we will have to evaluate an integral. The gamma of some number is the integral from 0 to infinity of x to the psi minus 1 times e to the minus x dx. And often that thing is not integrable. I mean, sometimes you can do integration by parts and you'll get there. But depending on what this exponent is, this thing is often, something you have to numerically approximate. I'm not sure what's going to happen here. I'm just forging on, sort of stalling because the math is getting hard. If I use this little trick that I wrote here, because I have 1 plus it, I thought that might be nice. Basically, I have 3 halves here. So I could write it as, 3 halves minus 1 times gamma of 3 halves minus 1. I don't know if that's helping me much. So we have 500 e to the minus 1 half times a half. And then we have gamma of a half now. And that's a very famous math problem. Leonhard Euler came up with a nice solution for this. The guy that E is named after is also someone who dabbled a lot with this gamma distribution. And he was able to prove that gamma of 1 half has a really elegant exact value. And it turns out to be the square root of pi. Would I expect you to know that? No. If you were a math major, maybe you would. Or maybe math history, you might know that because you'd be studying Euler. You probably would have had to evaluate the integral. Plug in a half, go from 0 to infinity of x to the half minus 1, e to the minus x dx, and solve this thing. Plug it into Maple, and Maple will do this symbolically and give you this nice Euler discovery. So it's kind of interesting. It's interesting in mathematics because it's pi is irrational, and then you're taking the square root of an irrational number, which often square roots are irrational themselves. So it's kind of interesting that way. Anyway, I'm sort of going all over the place. Uh, I lost my alpha, which is what I'm trying to solve for. Up in this step, I had alpha, and I just wanted it to be E so bad because I wanted to talk about Euler, but really that's still alpha. So let me fix that because that's what we were trying to do. We're trying to solve this thing for that parameter. So we have 500 equals alpha to the minus a half times the square root of pi. If you're interested in, the proof of that thing, it's check out the website here, Jekyll Math. I found it in a hurry, and it's actually pretty readable. They pretty much cover it in one page. It involves a bit of double integrals, but it's you can probably read through something like this even if you don't really remember doing double integrals and doing polar substitutions. I forgot most of that stuff myself, and I read through this and found it to be rather elegant and interesting, so maybe you would too. But if you don't, you know we would probably just use some sort of numerical software to get the answer to this. Doing a little razzle dazzle here. After you do some algebra, ultimately, pen wasn't working there for a second. You get a value for alpha. It turns out to be pi over 1,000,000. So pi times 10 to the minus 6. Just solve this thing, move the stuff over to the other side and then square both sides. Oh, you have to do reciprocals and then square both sides, but I think you guys can handle that. Now we know, through all that, now we know what alpha is. So now we can attack our Weibull problem. Remember what we're trying to do here. We're trying to find the probability of being greater than 800. So we're looking for this area. This is our R of 800, where R of t for the Weibull distribution is e to the minus alpha t to the beta. And we know alpha and beta after a lot of work and a lot of hand waving, really. I made up beta. Why couldn't I have just made up alpha? But I was stuck with, I said we were going to stick with the mean of 500 hours. So then we had to do all this work. Let's figure this out now. So R of t was e to the minus alpha t to the beta. So R of 800 is just plug it in. We don't have to do any integrals anymore. We already integrated the Weibull function. So it's actually easy once you know what alpha and beta are. It's e to the negative alpha. So in our case, pi times 10 to the minus 6. And then we have times 800 raised to our beta, which we chose to be 2, which is an increasing failure rate. You do your calculations there, you get 0.1339. To figure out the median, again, the probability that our time to failure is greater than some middle amount will be 50%. So we're just going to use, R of m equals 50%. So substitute that in. E to the negative alpha m raised to the beta equals 0.50. And we're solving this thing for m since we already know alpha and beta. Natural log of both sides, e to the becomes just negative alpha m to the beta equals the natural log of a half again. So m to the beta equals negative 1 over alpha, natural log of a half. And beta was 2, so m is the square root of this stuff. And hopefully the natural log of a half is negative so that we end up with something positive here. And it must be, I get a median of 469.7 hours. It's smaller than the mean. The mean was 500. If you look at the picture was, somewhat symmetric. So I'm not too surprised that the mean and the median were pretty close to each other. The thing is skewed a bit to the right, which indicates that that does coincide with this, median being less than the mean. And finally, we're on our last example for this one. We're trying to calculate the failure rate. And we're doing so at 800 hours. For the Weibull distribution, the function simplifies to alpha beta t to the beta minus 1. Again, that's on your formula sheet, so you don't have to, derive that each time. The hazard function for a Weibull distribution is just given by this. So check out your formula sheet. I don't know if I have a formula sheet already loaded up here. I don't. Well, at one point I posted a large formula sheet for you, so take a look at that and you'll see this formula on there. We want Z of 800 hours, so just plug in 800 for T. We're hoping that, I guess we're looking for, we said our failure rate was going to be increasing. Let's see what we get here. I don't want to rewrite what alpha was. What was it? Pi times 10 to the minus 6. Beta was 2. T is 800. Beta was 2. Stick that into your calculator. And now our failure rate is 0.005026 failures. I can't remember if we were doing hours or years, what we were doing. I think it was hours. Yeah, because our mean was in terms of hours. We had 500-hour mean. So at 800 hours, they're failing at a rate of roughly, 5 in 10,000. So obviously at any given time, these failure rates will be small, otherwise they'd all be gone long before 800 hours. So yeah, we've discussed 3 different probability models. In one of your labs, you'll also deal with how to come up with the alpha and beta, which doesn't require all this, algebra and solving gammas and knowing Euler constants and such. So there's kind of a neat exercise with that. So it's not this lab, it's probably coming up. So that's it for this unit, which was basically just, a review of our other units. We got to use the distributions that we know. We got to learn a little bit about, the idea of parallel and series, but basically that was just using the multiplication rule from our probability unit back in, what was it, unit 2 or 3. So, basically this stuff is a nice review of all the stuff of many of the things that we've done so far. We got to talk about medians, which we hadn't talked about in a while. We got to talk about complements. So yeah, a good review unit. The next unit we move into, we'll start talking about the central limit theorem and moving into inferential statistics. So stay tuned. That's it for now. I hope you guys all take it easy, and I'll see you next time.